Welcome to 6.4 Honors Pre-Calculus, Vectors and Dot Products. As I often do, I'm going to go ahead and jump right into these problems. You really need to see 6.3 and get the background on vectors before you move into here. We are going to, as far as this first page, and we'll come back and take a look at it, we are really going to focus on the first four items regarding what are referred to as dot products, but it is worth looking at this. If I have a vector u that has this is our x component, y component, and a vector v has these components, the dot product is defined to be, it looks like we're just multiplying them, but be careful, a little bit sneaky. We don't just multiply u and v and multiply u and u2 and v2 and get a new vector. We actually multiply the x's. This is our x, or like our x1, x2. We multiply our y's, like our y1, y2, and then we add the results together. We don't even end up with a vector at all. We just end up with a plain old number, which in vector land is called a scalar. Some properties of dot products might be worth taking a look at. This is a biggie, although I think it's a little bit silly. I think if theta is the angle between two non-zero vectors, then we can take cosine of it and find that. But why would we ever find this? What we really want to find is theta. So I prefer this formula as theta equals cosine inverse of u dot v on magnitude u, magnitude v. And if you get nothing else out of this assignment, that is that's an enormously useful product. Now this is how we define magnitude, but that's all discussed before. Somewhat likewise, if I v dot v, we get magnitude v squared, but we might want to think of this one as magnitude of v equals square root of v dot v, which, believe it or not, is actually just the Pythagorean Theorem, and we'll get back to that. Orthogonal means perpendicular in vector land. Not sure why they got a special name for it. Maybe I should research that. And all of the items below here, there is a workaround if we really understand mathematics, and I think you would like it more than if I went through this process, so that's what we are going to do. We'll see how this goes. This might be split over two different videos. Finding the dot product. Find the dot product of u and v. So u dot v is -4, 1 dot, we don't say times, 5, -4. One time I'm going to write all of this out. This would be equal to -4 times 5 plus 1 times -4. Or we get -20 minus 4, which is probably where I would normally just go straight to here, or -24. Okay, as we should have learned in 6.3, this is just the vector 2 to the right and 6 up, and this is the vector 3 to the left and 7 up. So if we take 2, 6, dot it versus -3, 7, we get 2 times, so this is u dot v, we get 2 times -3, -6, plus 6 times 7, 42, we get 36. And that's all there is to it. I mean, why would we do it? Well, there's a number of reasons, but the biggie's going to be coming up shortly. Here's some good news. We're to use our properties. If we take 4 times u, which is given as 2, 2, times v, which is given as -5, 3, just like if I was multiplying 2 times 3 times 4, I can multiply those in any order I want. And you could do this. You could multiply 4 into the 2, 2. We could dot product these. We could multiply 4 into the -5, 3. First, anything, I'm going to go ahead and just do it in the order left to right. So we get 8, 8, dotted with -5, 3. And we get 8 times -5, -40, plus 8 times 3, 24. We get -16. I think I'm going to set this one up this way. U, 2, 2, dot, 2 times v would be vector negative 10, 6, and that's supposed to be multiplied by W. So dot, I get negative 20 plus 2 times 6, 12 times W, or negative 8 times W, which is 1, negative 4, or we get negative 8, 32. We're back to a vector. So vector dot vector gives us what's referred to as our scalar. Scalar times vector just gives us a scaled vector. Negative 8 times as big. Now, finding the magnitude. We got a special new formula for this that says the magnitude of U equals the square root of U dot U. But then we also have old school where we could just draw this and say, here's my vector, it's 8 to the left, it's 15 up, making this side length negative 8, this side 15. Here's our magnitude right here, so we would say magnitude squared equals 15 squared plus 8 squared, or magnitude squared equals 225 plus 64, 289, magnitude equals 17. Now what if we did this formula? We'd say, okay, so the magnitude equals U dot U, that's square root of, that's 8 times negative 8, 64 plus 15 times 15, 15 squared, 225. And as you see, as I mentioned earlier, here we are, right back, Pythagorean Theorem. It's just Pythagorean Theorem. So you want to think Pythagorean Theorem? Great. Our physics people might be thinking in terms of magnitudes or in terms of our formula with our vectors, but it's just Pythagorean Theorem. Okay, so here we have a vector that would be, let's see, 6, negative 10, don't know why I put that here, it's this vector right here where this is 10 but negative and this is over 6. Pythagorean, our magnitude of U equals square root of 6 squared 36 plus 10 squared 100, square root of 136, let's see, that square root of 4 goes into there 3 times, and then we get, 4 goes in there 3 times, we get 1, 12, 1, 6, let's do that, sorry, just show that over here. I've got my phone going off in the background, a little bit distracting to me right now. We go in 3, we get 12, we get 1, we get 6, goes in 4 times there, 36, so we get 2 square root of 36. All right, there we go. Find the angle between, find the angle theta between vectors. Now here is dot product at its best. I'm just going to rewrite, excuse me, this formula that says theta is equal to cosine inverse U dot V over magnitude U magnitude V. So here we go. Theta equals, now I could do some of this in my head. I'm going to encourage you not to, and you're going to see why. U 4 dot V negative 2 0 over magnitude of U. And here's why I don't. This 4 lays out really nicely. Those are the two legs. Those are the two legs of a right triangle. So the magnitude or the hypotenuse would be 4 squared 16 plus 4 squared 16. The magnitude of V would be negative 2 squared 4 plus 0 squared 0. And now I get cosine inverse of, let's dot this. I get negative 8 plus 0 on square root of 32 times square root of 4, which of course I could simplify this and simplify this, but I'm going to go to calculator anyway. So cosine inverse of negative 8. I'm actually going to write this as square root of 32 times 4 just to simplify the process with the calculator. Now, again, I could just make this 2. I get that. I could pull out a 16 as a 4 root 2 here. I get that. I could do a lot of simplifying, but cosine inverse, we're going to our calculator anyway. Second cosine inverse of negative 8 divided by just the single square root, 32 times 4. And we get 135 degrees. Now, such a nice angle that we're used to, such a nice angle that lives right over here. Let's take a look. We're at 4, 4. 4, 4 would be right here, and negative 2, 0 could be right there, and sure enough, that should be the same angle as this 45 right here, 135 degrees between them. So there's a problem that had we drawn this, sketched this out first, we probably wouldn't have gone through this process, but not so nice on this one. Okay, so here we go. This is 7, negative 2 in component form, negative 8, 6 in component form. So the angle between is cosine inverse 7, negative 2 dot negative 8, 6 over magnitude or square root of Pythagorean 49 and 4. Square root negative 8, 64 squared, and negative 8 squared, and 6 squared. And we get cosine inverse of, let's see, I'm just going to cheat up here, negative 56 plus negative 12, negative 68 on big square root 53 times, that's 100. Yes, we could write it as 10, but I'm just going to put it 100 under the radical. Here we go. Second cosine inverse negative 68 divided by 1 big square root, 53 times 100. And we get 159.08-ish. If I was to sketch this, let's take a look and see if that seems reasonable. If I was to sketch this, we would be 7, negative 2, maybe something like this out here, and negative 8, a little further, up quite a bit more, somewhere right in there. And that seems somewhat reasonable that that angle is approaching 180 degrees. So I feel pretty good about it. Okay, interesting little problem here. Angle between these two. What we would have learned on the previous section is that this is, assuming you didn't see the previous section, let's go through this. Cosine pi on 4. Here's pi on 4 right here. Pi on 4. We're a 1, 1, square root of 2. This is square root of 2 on 2. We get square root of 2 on 2 I plus sine pi on 4, square root of 2 on 2 j. 2/3 pi. Right here, a 1, a 2, a square root of 3, but left. That is x on r, negative 1 on 2, I, plus y on r, square root of 3 on 2j. So u is square root of 2 on 2, square root of 2 on 2. J, or v, is negative 1/2 square root of 3 on 2. Well, let's just sketch u and see. Maybe it's a maybe since they're nice angles, it'll work out without even going to the formula. So here is square root of 2 on 2, 2. It's right here. Square root of 2 on 2, square root of 2 on 2. And here is, those are 45 right here. And here is negative 1/2. Oh, look at this. We're right back up to this angle. negative 1/2, square root of 3 on 2, but this was a 120. We're the same exact angle that we were. This is a 120. Let's see, so we're 120 minus this 45, 120 minus 45, we're at 75 degrees. Nice little opportunity. Notice we're just the angle between, it's just 2/3 pi minus pi on 4. And we had a little bit of discovery on that back in 6.3. Okay, moving right along here, see how we're doing time-wise. I'm in pretty good shape for right now. 31 through 34, graph the vectors and find the degree of measure and angle between them. So let's sketch that over here. Quite a bit of room left, a little bit down, quite a bit left, and a little bit up. Maybe something like this. -7, -4, and -8 a little bit further, and up not as far. So maybe about right in here. And what we're looking for is this angle. Somewhere, I don't know, like 45-ish or so it looks, if my scaling was good. So this is -7, -4, -8, +2, and theta is cosine inverse -7, -4 dot -8, 2 magnitudes of these, square root 49 and 16, hopefully we're seeing where those are coming from, times square root 64 and 4. So theta is cosine inverse of, let's see, this would be +56, this dot, plus -8, 48 on big square root of 65 times 68. Second cosine. 48 divided by 1 big square root of 65 and 68. 43.78. And what did we think? Oh, I think I said it looks like it's going to be pretty close to a 45. Looks pretty good. Use the vectors to find the interior angles of a triangle. We got a little bit going on here. Left and down, right and way up. Pretty far right, so I need a lot of room this way. Let's see how we're doing here. -3, 1, 2, 3. -4, 1, 2, 3, 4. Right 1 up 1, 2, 3, 4, 5, 6, 7, and right 8, 1, 2. That's 3, 4, 5, 6, 7, 8. So we've got point. We'll refer to this one as A. This is not a vector. It's just an ordered pair. Use vectors to find the interior angles of the triangle with the given vertices. Let's put B at 1, 7. Let's put C over at 8, 2. And my triangle looks like that. Sure, I don't have the y-intercept right there, but there's our triangle right there. We're supposed to find the angles using vectors. If we didn't, we could find the distance, find the distance, find the distance. We could have side, 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 and start our law of cosines, law of sines. That would be a possibility. But let's see. Let's go for angle A. For angle A, I need vector AB going this way, and I need vector AC. Let's see, to get from A to B this way, I've got to go, let's see, let's do it here. I've got to go to the right 4, and I've got to go from -4 up to 7. I've got to go up 11. To get from A to C, I've got to go from -3 over to 11 to the right, or over to 8, increase of 11, and from -4 up to 2, an increase of 6. So angle A is cosine inverse of 411 dot 11.6 on square root of 4 squared plus 121 times square root of 121 plus 36. Cosine inverse of, let's see, we've got 44 plus 66, 44 plus 66 110 on big square root of 16. I don't know why I didn't square this one. 16 and 121, 137 times 121 and 36, 157. And here's angle A. Second cosine inverse. 110 divided by great big square root. 137, maybe just big square root, times 157. And angle A, about 85 degrees, which I am not a believer there. This is probably good you see this because it reinforces checking. I promise you, I did not intentionally make a mistake here. Let's see what we've got. We've got 4, 11. I like that. We're over 4, we're up 11. We're over 11, we're up 6. I like that. I just don't believe this angle's 85 if I drew this anywhere near scale. So, dot product. We get 44, 66, 110. 4 squared, 16. 11 squared, 121. 137. 11 squared, 121 plus 36 squared, or 6 squared, 36. 157. I've got, oh, I'll bet you saw it. Sure enough, I've got cosine of 110. It was calculator entry error. I couldn't be happier that that happened. Maybe I'm just trying to put on a smiley face on this one. But I did check my answer, 85, with my diagram. Now, my diagram is not perfect, but I just did not believe that was 80, 85, 86 degrees. So let's go second enter. Let's go back, second insert that 0. And enter. 41.4 seems believable. And now we need to find another angle, and then we can subtract from 180. I'm going to get the ball rolling on this one. Let's go for angle B. For angle B, I need this vector. It's going backwards. And to get from B back to A, the x's went down 4, or left 4. The y's went from 2 to negative 4, or excuse me, from 7 to negative 4, went down 11. It's not, I should have a cosine inverse here. Let's go angle B equals cosine inverse negative 4, negative 11. It's not a coincidence. Negative 4, negative 11, B to A is the exact opposite of A to B. Now we need B to C. Let's see, vector from B to C. From B to C, the x's increased 7, so dot 7. The y's decreased 5, negative 5, all on square root of 16 plus 121 times square root of 49 plus 25. At this stage, I'm going to dot, dot, dot. We should be able to go through that process with our calculator and then take angle B, angle A, subtract the sum of those from 180, or 180 minus this angle, and we've got angle C. But don't forget, as we just saw, probably want to check the validity. I mean, I'm expecting something maybe close to 90, if perhaps not a little bit under, for angle B with our dot, dot, dot. All right, here we go. Going to try to run through this thing. Orthogonal, remember, means perpendicular. And there is a rule on the front page on the orthogonal that talks about if they're orthogonal, the dot product equals 0. And that might come in useful, but I'm going to go back to algebra land for this problem. Here I've got two vectors. We understand in this vector the x changes by 15, the y changes by positive 9. That means our slope of u is change of y 9 over change of x 15. That's 3/5. The slope of v, the y changes negative 3 as the x changes negative 5. That's 3/5. These vectors have equal slopes. Therefore, they are parallel. Had this been negative 5/3, they would be perpendicular. If it wasn't equal to or opposite reciprocals, neither. Oh, that's pretty useful. Now, I do think the dot product formula might be useful here that says if u dot v equals 0, then orthogonal, which we think perpendicular. Find the value of k such that the vectors u and v are orthogonal. Well, this vector u, negative 3k5 dot 2, negative 4, if they are orthogonal, should equal 0. Excuse me, I need a little backing here. I'm on wood grain. So dot product, negative 6k plus dot product, negative 20 equals 0. Negative 6k is 20. K is 20 on negative 6. K would have to be negative 10/3. Okay, a lot going on problem 74. This is where, if you don't follow what I'm doing here, you're welcome to, obviously, if I have you in class, you can ask some questions on it or do some research outside. This can be done with all of this definition of vector components and this projection topic. And a projection is kind of a shadow, and we're going to kind of refer to that in here. Sport utility vehicle with a gross weight of 5,400 pounds is parked on a slope of 10 degrees. Now, I realize this is more than 10 degrees, but it gives me a little bit of working room here. So we've got a 5,400 pound SUV that has a force going down this way, and there's no magic about stopping that right here. I'm just going to for neatness. It has a direct downward gravity force of 5,400 pounds in this case. Now, what we need to understand is, as this gets steeper and steeper and steeper and steeper, it's going to take more force to hold this up. But right now, the force can be divided into components. The total force, that's like the magnitude, is 5,400. But we can put this into components like this and say, here's the force of that it's trying to go rolling down the hill and complete our right triangle here. This would be the force perpendicular that they're going to ask about in a little bit. Find the force perpendicular to the hill would be this right here. So I'm going to refer to this length as A and this length as B, and I'm going to redraw that, try to do it similar here. Looks something like this, where this is 5,400. Here's a right angle. This is A, this is B. B is the force that this thing is applying downhill, so we would have to push against that with the same force to keep it from rolling down the hill, and A is the force perpendicular to the hill. The problem is I only know one thing about this right triangle, but this 10 degrees is a player. Let's watch this. 10 degrees is an element of that triangle. This is a right triangle right here, and therefore this right in here must be 80 degrees, making this 10 degrees. And now we're in business, SOHCAHTOA. You could use the 80 or the 10. I'm going to use the 10. So the force going down the hill would be B. So from sine, B is the opposite. We know the hypotenuse. From 10 degrees, excuse me, B is the opposite. 54 is the hypotenuse. Sine of 10 degrees should equal B on 5,400. So B equals 5,400 sine of 10 degrees. Sine of 10 degrees is pretty close to 0, so there's not a lot of force going downhill, but there is some. A, from 10 degrees, cosine. Cosine of 10 degrees equals A on 5,400. Now, cosine of A is, let's wrap this up. A is 5,400 cosine of 10 degrees. Cosine of 10 degrees is pretty close to 1. So A, the force perpendicular, is pretty much most of the 5,400, because this is almost 1. And that makes sense because the ground is really pretty flat. I'll leave the calculator work there for you. And final problem. A ski patroller pulls a rescue toboggan across flat snow surface by exerting a force constant of 35 pounds on a handle that makes a constant angle of 22 degrees with the horizontal. So here's our toboggan right here. And we are pulling that thing at 22 degrees. And the problem with that is we got a force of 35. The problem with that is the whole 35 pounds is not really being exerted to pulling it along the ground this way, because some of that is lifting. This much of it is actually lifting. This much of it is actually pulling. We've got that right triangle components again. If we wanted to be totally efficient, we'd pull 35 right in this direction, but it might be uncomfortable to bend down and pull it in that direction. So we throw it over our shoulder, tie it around our waist, whatever. We're supposed to find the amount of work done. Work equals force times distance. We need the force applied. The force applied on this toboggan as far as pulling it sideways is not 35. It is this distance right here. This is really being wasted in regards to pulling it forward on the flat snow. We want to know what A is. That's our force. The distance we're going to cover is 200. Now imagine we were pulling it on with a force of 100 and we moved it 0. Oh, we worked. I mean, we pulled it with a force of 35 for 10 hours and didn't move it an inch. We didn't get any work done. We worked, but we didn't accomplish anything. Work is force times distance. So the distance is easy. Work equals something times 200. The force is A. From the 22 degree angle, A is our adjacent, 35 is our hypotenuse. Cosine of 22 degrees equals adjacent A on hypotenuse 35. A is 35 cosine of 22 degrees. Again, 22 is closer to 1 than it is to 0, so we're getting most of the benefit of pulling at 35, but we're not getting the whole 35 there. But we are getting the whole 200. I will leave the computation of that to you on your calculator, and that wraps up section 6.4. Pretty mechanical until those last two little problems. I think particularly 74 may warrant some more discussion, and certainly you'll have an example like that if you do the homework set. Couple examples of work problems as well. So good luck. As always, let me know if I can help.